Thank you very much for that generous introduction. I'm not sure I deserve it, but it's very much appreciated. And welcome, everyone. I can see so many friends and colleagues here. Thank you for coming on what must be a cold night. But I think we're going to have a wonderful series of lectures. The ones that are coming up later about birds in the Kimberley, rock art, frogs, they're a wonderful series, and I'll do my very best to kick it off. I think throughout the years, we've been running these lectures since 2010. They're becoming more and more popular, very important. As chief scientist, and of course the museum is far more than science, but much of it is, my motto was do science, translate science, and communicate it. The museum does just that. You do wonderful work, you make sure you interpret it for West Australia, and then you communicate it. We're very proud of our museum, and I'm thrilled to be here as part of it tonight. So what I'm going to do is talk about one of my favourite things, and that is vision, because I've worked throughout my life on how the eye works and how to put it right after injury and damage. So I'm really picking up some of the things that I'm most interested in, and I hope you are interested in some of them too. But let's start with a little tiny bit of physics. It won't go much further than this, I assure you. But you find waves that go right from the gamma waves that are really close together, the X-rays, through the light we can see to much longer ones, the microwave waves you use to heat up your coffee, and the radio waves. So as you go along the electromagnetic spectrum, from very close together to very stretched out, you get many different properties. And the two groups of these wavelengths I want to talk about tonight are the only two that reach the surface of the Earth. All of them bounce off, except those in the visible spectrum and a little bit out towards the infrared and ultraviolet and radio waves. So I'm going to be talking about these two groups, the ones that we experience here on Earth, ones we can appreciate, but ones that also we need technology to help us to identify, in other words, the radio waves. But let's start in that middle bit, the central tick, because today's talk is going to be about vision, vision with our eyes, eyes of other creatures, and then using radio eyes. So my first question is, do we see the same colours as birds and other animals? This little chap at the bottom there, this shrimp, probably has the best colour vision of any species on Earth, and look how beautifully coloured he is. But I'm going to restrict my talk today to the vertebrates, starting with the fish and up to humans. And there's Harmony. She's one of the birds that's been raised in the recovery program for the black cockatoos. Found as a baby, can't be released back into the wild. And of course, you can see a tiny bit of red on her tail. Is that significant? Well, that would lead you to think that birds can see colours, and rather many brightly coloured ones. But what do they see? And is it the same as us? So, tiny bit of neuroanatomy here. Here's the eye, cut in cross-section diagrammatically. The light comes in from the far side, focused by the lens, in some cases like me with the help of a pair of spectacles, and falls on the light-sensitive sheet, the retina that lines the back of the eye. And that has numerous cell types in it, but the ones we're most interested in are called cones because they're vaguely cone-shaped. And they're the cells that transform colour information into electrical activity and send it off to the brain. Interspersed with them are things called rods, and the rods detect only black, grey and white. So at night you'll be using your rod vision, and during the day you're using your cone vision. Within these cones are pigments. They're not pigments you can see, but we call them pigments because they resonate when light of a particular frequency, in other words, a particular colour, hits them. The ones that have a pigment that respond to red light jiggle only to red. They convert that light into electrical signals. They make their way to the brain, and you see red. And similarly for other colours. So depending on how many visual pigments you have tells you how many different colours you can see. And the little shrimp I showed you before has 22. So he probably has absolutely splendid colour vision. So how come we get to see different colours? As I said, we have these pigments inside our cones. If we could turn back the clock and see what was happening way back as the fish evolved 370 million years ago, what colours could they see in the ancient seas? Well, of course, we can't look to find out yet. We can't do analyses yet of fossils to the extent of picking out those different pigments, but we can get an idea by looking at their descendants, the hagfish and the lampreys. And from that, we're pretty sure that they had 4 different visual pigments, one sensitive to red, one to green, one to blue, and one to ultraviolet. And they're not completely finely tuned, so the red one sees a bit of yellow, and the green one sees a bit of blue, and the ultraviolet sees a bit of far blue as well. So they overlap to give, presumably, these ancient fish a wonderful view right through the colour spectrum, including, of course, ultraviolet that we can't see. What happened thereafter? Well, the fish, as they evolved to the modern form, retained these 4 visual pigments. And to give you an example, to convince you, I hope, that they can see colour well, I'm going to show you an experiment that was done on a little ray, related to the sharks, of course. And this is to illustrate his ability to see colours. So in comes our little ray. He loves scallops. If he goes to either to the coloured square rather than to a black or white one, he's rewarded. Yum. So, of course, you have to move. You have sometimes to put the colour one on the left or the right. They have to learn that it could be either side. In he comes again. And there's matched brightness. So if he could only see grey, they'd look equal. Okay. He's touched it already. Come on, experimenter. I deserve my scallop by now. I'm touching it for the 3rd time. Lunch. So these are the sort of experiments you can do to show that animals can see colour. There are lots of others. I'll tell you some in a minute. Yeah, it's very fond of that pink one. So not only the fish, but the amphibians, the reptiles, and the birds retain these 4 visual pigments, seeing from the ultraviolet right through to the red. And that's hardly surprising, because many of them are very brightly coloured, as you can see. I can't talk about the birds for too long. They're not the main subject of this talk, but they are absolutely fascinating because they go into hyperdrive for colour vision, because not only do they have these different visual pigments in their cones, but they have within them too oil droplets, shown diagrammatically here as just grey, but when you look in real life, and this is sort of a helicopter view down on the retina, you can see that those oil droplets are very brightly coloured, so they intensify the colour you see. It's like wearing rose-coloured spectacles, but in this case you can see it's also gold colour spectacles, presumably to enhance those colours. And they're pretty well unique to birds. Other species have them, but not as brightly coloured. Okay, we've come up the whole evolutionary tree, and now we're getting to the stage where mammals started to evolve. And here I'm treading on very dangerous ground because we have an expert sitting in the audience on the dinosaurs. And of course, if you get a chance to go and visit the dinosaur exhibition at the Perth site, please do. Dinosaur Discovery, 75,000 people have been already. It's going to be our absolutely top seller ever. It's a brilliant exhibition. I recommend it to you. But current knowledge suggests that the dinosaurs were active during the day. And if you were going to survive as a little mammal, you had to only come out at night, otherwise you were lunch. And they were quite small. They couldn't evolve to be very big, the first mammals. Presumably they had to scurry and hide very quickly. If you don't have to be out during the day, you don't really need colour vision. Just think of the thing you see at night. Apart from the very brightest moonlight, everything is shades of black, white, and grey. So as a result, the primitive mammals lost 2 of these pigments. They lost the one for blue and they lost the one for red. They were restricted to seeing in green and blue. Now, the mammals that evolved after them, the dogs, the cats, the camels, the hippopotamus, not that anybody's tested that one, I'm sure it would apply, they all have this restricted range of colour vision. They'd have done great if they'd visited the paintings by wonderful Picasso in his blue period, painted as a teenager and so exquisitely. But they wouldn't have done well for more brightly coloured and diverse colours. So when people say to me, but my dog can see a red ball, they can see a ball, but they won't see it as red, and they're probably more interested in it when it moves, because to them, it's just going to look greeny-grey. And that might make you wonder about other colours. Well, it was jolly important if you want to eat blackberries to know what colour it is. And if you're growing your tomatoes, you want to know whether they're green or red. So actually the ability to see red is rather important to get a good diet if you're relying on ripe things. Also, of course, forget about a red rag to a bull, because a red rag to a bull is a green rag or grey, but at least it moves around, and that's what's going to annoy a bull. But something amazing happened. As the mammals evolved, we got to the stage where we started producing the primates. And then an extraordinary evolutionary feature happened. Somewhere, as the DNA divided to give 2 copies of the pigment for green and put 1 in each of the daughter cells, the sperm or the egg, and go on to the next generation, the copy was changed. There was a mistake in the copy. But it was a brilliant mistake because it meant that copy was then sensitive to red. We had reinvented the red gene that had been lost at the time of the dinosaurs. And again, of course, important to distinguish ripe from unripe fruit. And in the case of Australia, newly formed leaves, which are often beautiful red rather than the darker green. More of that in a minute. And the primates, of course, have made the most of the ability to see red, as this mandrill will show very clearly, or if we move to the other end of the operation, well, they look pretty good to a male baboon, I can tell you. Those are females saying, come hither. Obviously, red is an important part of all primates' life, and I'm sure Eve, if she did look down at those apples that were so carefully adorned onto Adam, would realise how red they were. So we can see red and we take it for granted. But the standard dictum was only primates of all the mammals can see red. And this was in all the textbooks. I didn't like that idea very much when I read it in the textbook. It didn't seem to me that it was the whole story, because it was only looking at those placental mammals, the ones that evolved mainly in the Northern Hemisphere and in South America. It ignored the South American marsupials and the marsupials in Australia. Nobody had really bothered to look properly after the dictum went down that they couldn't see colour. And the reason they thought they couldn't see colour was the first explorers would collect any animals they could, preserve them in any way they could, and often it was by putting them in things like barrels of rum and sending them back to Britain. Or other places. France was another one that did a lot of analyses. Well, by the time the animal's eyes had been preserved in rum for about 6 months and battered its way back to Britain, it's hardly surprising that the eye was in such poor condition that those cones I showed you at the beginning had actually just broken apart. You couldn't see them. And the scientists made the mistake of saying if you couldn't see it, it wasn't there. Well, you can't always assume that. And in fact, as we went on to show, they were quite wrong. But the main reason I thought they were wrong was because we live in such a wonderfully colourful world. I mean, the amazing work that the curators do at the museum to document, to discover new species and to protect the ones we have. It's just superb work. And here are some of the mammals that live either exclusively or mainly on flowers. And they're brightly coloured flowers, and many of them in the Australian environment are red. So it seemed to me very unlikely that our marsupials were going around with that poor vision that the dogs, the cats, and the bulls and all the others except the primates had. So we set out to test it. Now, the way we tested it originally was with a technique called microspectrophotometry. Just to explain a little bit of the background to this, what you do is you take a few cells from an eye, there are billions there, so it's easy to just get a small sample, and you put them in a machine where you shine a very thin beam of light through one of these individual cones, and you see if the light gets out the other side. If it does, that cone isn't interested in that colour. But if it's a cone, say, with a pigment that absorbs red, then if you put red light across, it won't escape to the other side, it will be absorbed and transformed into electrical activity. So because these cones are so tiny, that beam of light is 1/30th the width of a human hair. You have to do all this virtually in the dark, not to bleach the samples. And after a day, when you come out from there, you feel pretty ragged, but with some brilliant results. Now, one of my problems was that I didn't actually have a microspectrophotometer. And there were only 6 in the world, and they cost about, in those days, this was about 10 years ago, about $300,000. Now, I hadn't actually worked in colour vision before. I'd worked on recovery of the optic nerve from damage. So it was a bit of a stretch. So I needed a microspectrophotometer, and would you believe it, there was one. There was one sitting in one of the universities in the eastern states, and I won't say where, but it was owned by a gorgeous man I'd known back in Edinburgh when I'd been a PhD student. He had built this apparatus, he was retiring, and he very much wanted to give it to us because he knew we would make very good use of it. So, wonderful, we're going to get a microspectrophotometer. We get a room ready, we get it repainted, we get a label on the door, we've got our experiments all planned. We've even found a company who would transport it across the Nullarbor for us without charge. And then I get a phone call to say, Lyn, there's a bit of a problem because the university's discovered that I'm donating it to you and they want it valued first. No, this is it. It's never going to come. So don't worry, I've got a plan. So the next day I get another phone call. It's on its way. It's probably past Port Arthur now. I said, how did you do that? Did you really get a proper professional valuation? He said, absolutely. I got the local scrap metal merchant in. $4,000 of scrap metal. Get rid of it. But it has served us in very good stead. And now the lab is run by Premier's fellow Professor Sean Collin, and it's actually the top comparative colour vision laboratory in the world, and I can say that with great confidence. So good on you donating that microspectrophotometer. So from that, we looked at little species such as this dunnart. We looked to see the colours, the pigments in their eyes initially. And we did a lot of behavioural studies, rather like the one I showed you with the little ray. The temptation for a dunnart is juicy crickets. They absolutely love if you show them 2 lights, one that's a particular colour and another colour, and you train them, for example, to go to the red one. They get a reward when they do. The cricket, the reward, they just love doing it. So we tested them many, many times. And the result was we were convinced they could see red and green and they could see ultraviolet. And in fact, we couldn't. So it was very interesting. You'd have 2 things that looked identical to us, but not to them, and they could know which to go to. We did lots of other studies. For anyone here who's a physiologist, just to tell you, we did studies with him in histochemistry to look at the chemistry of these things. We looked for the genes because we know the sequence of the amino acids in the protein. We can work out from that the sequence in the DNA, so we could look for that. And we even did behavioural studies. This is a delightful little honey possum. You might wonder what's happening to it. It's actually a wild one. We trapped it just overnight, and we put this little, you can see the radio transmitter on it. My postdoc who did it, I think she is another Dr. Dolittle. Wild animals love her. That is not anaesthetized in any way, sitting quite happily. And we could track where they went to see when they were going on flowers. We were convinced they'd be going on ones that were yellow, orange, and red. and they definitely were. And after 2 days, that would just drop off, and we would just collect the transmitter to use again. So from all these studies, we realized that marsupials could see all the colors we can, including red, and they can see more because they can see ultraviolet. So the top row is the colors that we humans see, and at the bottom is what marsupials see. So this same flower that looks to us just one color, to a marsupial or to a bee, for example, would have those guidelines to get you into the middle, the action part of the flower, where the nectar would be, and expose you to the pollen as you went in. Here are two other common objects. What would they look like to a kangaroo? Well, you'd see a lot more detail in the feather there than we ever see. And of course, you'd see another colour in the rainbow. And I can't colour that in to show you what it is because we can't see ultraviolet, but there'd be another colour in the rainbow on the innermost side, which other species would be able to detect. So, colours. Colours are important in life, but other aspects of vision are important too. How could we restore vision after it's been lost? It's described as the most precious gift after that of life, and I think that's probably right. So I want to tell you about a program that I'm really honoured to be part of. It's funded by the federal government, and I'm on the board to oversee the science. But I have to take a little step back first and tell you about the Bionic Ear. I think everybody knows about the absolutely wonderful discovery by Graham Clark that you could actually restore hearing to those who are profoundly deaf. I actually asked a lady recently who became deaf at the age of 40 in Rockingham and had a cochlear implant. What does it sound like? You can't really ask children because they find it hard to describe, and of course, especially if they haven't heard properly before. She said it sounds like a cross between the Chipmunks, remember the Chipmunk songs, and an answer machine. But compared to not hearing, it's amazing. You have to learn certain sounds. It's hard to hear s from ch from th, but you can do it. It just takes a little bit of extra training. But she said the wonderful thing about it is that her husband's a terrible snorer and she turns it off at night. Well, the way it works, and you can see it here on this young man, is, and probably got a pointer here, have I? You never know. Do you think there's a pointer? Oh, yes, there we go. So this device here that sits at the back picks up the sound, a sort of little detection device, and converts the sound into electric pulses and sends it round to the surface of the head here. A message goes across to a device inside of the skull and down to the ear. So this is what it looks like. This is the part that does the receiving of the sound and transforming it into electrical activity, sends it by a wire up here to the surface of the head and inside. And this is what's inside. So when that signal sent by radio waves, just the way you get 7:20 in the morning if you're listening to Ian Cameron, it goes across here to the implant, and then there's a little wire that runs all the way down and coils inside the cochlea, the part of the ear that if it was working would have tiny hairs in there that will respond to different frequencies of sound from deep to high and send the electrical activity to the brain. So that's the way a cochlear implant works. And hugely successful. So many people around the world have had their hearing restored. I've worked with 5 little girls down in Rockingham. This young lady at Baldivis Primary School, her life has been given back to her by a cochlear implant. She's now integrated with all her friends. She's doing great at school. And would you believe it, her mum, in extra efficient way, made sure that this young lady and her younger brother had a cochlear implant on the same day. Wow, that was a brave thing, but it's worked for both of them. But could we do the same for vision? It's a much bigger ask, far more complicated organisation of the eye than the ear, and much more complicated in terms of how much of the brain is dedicated to analysing vision. Do you remember when this gentleman first became the Prime Minister? He had 1,000 clever people along to come up with lots of clever ideas. He had Kate Blanchett there as one of them. And one of the clever ideas was, can we do for vision what we've done for hearing? In other words, could we do bionic eye or bionic vision? $50 million was committed by the federal government, and 2 groups were selected to do this absolutely amazing task. It's not going to look like that on the left. And I discover when I take that to schools, people look blankly at me, so nobody's watching the old Star Treks anymore. But this is what it will look like. Basically, you need a camera to look at the world, but you don't want to walk around with a camera sort of stuck to your forehead, so you disguise it somehow inside a set of spectacles. But they're there merely to carry the camera. The camera detects what's going on in the world around, transforms that light into electrical activity and sends it down to a processor that cleans it up and makes sense of what you see. And I'll show you an example in a second of the sort of analyses that it's doing. So what happens next depends where the damage is. If the damage is in the eye, but the intact wiring can take the message from there into the brain, that's the best way to do it, because it's using all the circuitry in the brain as much as you possibly can. So it'll apply when the retina is defective, and that would be, for example, if those photoreceptors you saw, the rods and the cones, had degenerated. And there are conditions, genetic diseases and others, where you lose those photoreceptors. This would be a great approach then. So what you would do is, the signal that's come into the camera, gone down to the processor, there would be a little wire that goes back inside the eye and stimulates a series of zones across the back of the eye, and that would send electrical activity down to the brain. So you're taking the outside image of the world, you're reducing it to aspects that will be useful, you're then applying that electrical current to the optic nerve and off to the brain. But 4 out of 5 cases of blindness, that just won't work because the wiring has become defective. And that's the program I'm more involved with, needing to get direct input into the brain. And as I say, 4 out of 5 cases will need that. So macular degeneration, and of course with an aging population, this is becoming increasingly common, age-related macular degeneration, glaucoma, retinal diseases such as diabetes, where you get leaking into the eye and the retina is destroyed, and just a small number up here, the ones that can be treated by the eye device. As I say, great if they can, but most of them can't. So this is where the direct-to-brain one comes in. I think it's a wonderful example of getting university, hospital, and local small to medium-sized industries on board to do absolutely world-leading stuff. So it's involved a huge collection of people, not only those in industry, but you can see a list there of all the teams that have to be working together on this. It's just been a brilliant program pulling it all together. And this is how the one works that's sending direct to brain. So imagine you're looking at a chair. Just as before, you have the camera that's suspended on a set of spectacles. And again, it's extracting information from the visual world, turning it into electrical pulses, going to their version of the processor to clean up the electrical signals, then back up, as you saw with the boy with the cochlear implant. You have a similar device on the back of the skull, the back of the head, to the one you saw there. Again, sending the information wirelessly across. And in this case, it's going to go onto a series of tiles that have on them tiny bristle-like structures that are literally going to stick into the brain and directly send the electrical activity to those cells in your brain, in the part of the brain that detects vision. In other words, the visual cortex. I'll show you where that is in a sec. This is what our processor looks like. A lot of work has gone into developing that. And these are some of the early tests that were done to try and develop, obviously, larger devices, but relate them to the final product. So what are you going to extract about the world? And it was interesting, last week I was talking to a group of students, and they all said the most important thing was colour. Colour's your life, I guess, but just think, with a black and white TV, you can follow the plot very easily. So we're not attempting at the moment to build any colour vision into this system. We're just going for light there or light not there, black and white, in other words. So the traditional approach to interpreting two guys here, one of them waving his hand, looked a bit like that. And we thought, well, it's very difficult to make any sense out of that. And even with the edges in place, it still looks a bit difficult. You wouldn't really know it was people. But what we did at an early stage was to go out and talk to people who are blind and say, what are the most important things about the world that you would like to see? And they all say faces. Preferably you'd like to know who they are, but even to know there's a face there. And things like doors, so you could navigate around in the world. And I can understand that. It's great that I can see each of your faces, and it's jolly good I can see the door in case the alarm bell goes. So you'll see that's what they most want to do. So we set about, the clever scientists over there, doing it a different way, where they concentrated on faces and they concentrated on movement. So if this arm is moving, you want to know. If something's coming into your world quickly and it's going to change what you can, your environment, you want to know. Out of left field is the sort of thing you need to detect. So this is the way our processor works. That's the image that we're hoping people will get. I know it's not brilliant compared to how well you and I can see, but compared with not seeing at all, the feedback we have is that that would be extraordinary. And when you think about it, not only can simple little cameras tell you where faces are, they can do that already, but when you come through customs, you line up in front of that machine and it knows whether it's you or somebody else. So there's an awful lot of information you can extract about faces. So at the moment, we can't say whether this is Alec Coles or whether it's Diana Jones, but in a few years' time, we might be able to have a little sign that says who it is, because we could analyse the faces more as we can build more into the software and hardware of the whole system. The brain's going to have to learn to interpret these signals, just the way the people who have bionic ears have to learn and listen to know sh from ch. Same way, we're going to have to teach in some way, we don't know quite yet how, to interpret the world and make the most of the signals. Before we could go into a patient, we actually had to look at the structure of their brains, because if they hadn't had vision for a while, the parts of the brain that respond to visual input will have shrunk. So you can't take the standard measurements of a brain, you have to go back in and look at all the wiring. And that's what we've been doing at the Centre at Monash University for Biomedical Imaging. So you can see all the different pathways in the brain, shown here with false colours, but to show you the complexity. And here we can see some of the images as they have come off the PET scan to tell us the structure of the brain in someone who has lost their vision. We're going into the back of the brain here. The eye would be out here. The normal visual pathway would come to this point. That's the first point at which vision is conscious. That's when you start knowing you're seeing something. But once it's analysed that, it goes off to all these different centres. Some will analyse faces, some will analyse moving objects, some will look at the angle of the lines, some will look at disparity between the images from the two eyes that give you the sense of depth. So we're hoping that by going in here, which is the real sort of first port of call for all the input from the eye when it really is beginning to make sense, that all these other circuits then can pick up that information and make the most of it. And here is the brave surgeon who is going to put all this into action. We're going into the first client. We've had so many volunteers, you can imagine, 2,000 people put their hand up. We've had to be very selective. We can't promise them what they will see. We can't even promise them whether the device will work in the long term. But they are so keen to be part of this to see if it could work. So watch the news next year. Early to mid-year, we will be going into our first patient client, and only then will we know whether this technology is going to be of value. But we're very excited, and we very much hope it will be. Because I think not only will it transform life for people who are born blind, it will also save money. Anyone with a guide dog costs $120,000 a year by the time you've added up breeding the dog, training the dog, how long it can be with you, and so forth. So if this gave the equivalent or more than having a dog, people would like that. And they also, many feel that being with a dog is a little bit of a social stigma, and this will put them more back into the real world. And certainly sitting at the dinner table, to know who is where, you can't get that other than with a device such as this. So, as I say, watch this space, and I think just like the cochlear implant, if it works, there's an income for Australia too, and that can't be bad. Let's hop along the electromagnetic spectrum. From this part here, we've talked about colour, we've talked about how much we could restore it in people who have lost their sight. Let's whip along the electromagnetic spectrum out to the radio waves. And of course that brings me to astronomy. Australia has the longest continuous culture of any country in the world. Probably the first astronomers were the first Australians to step onto our vast continent and navigate it. To do it, looking at the stars, knowing the time of year, knowing the time of night, that's just an amazing achievement that most of us couldn't begin to do. So the stars were very important and always have been to the Aboriginal people. And isn't this an absolutely beautiful work of art? And the relevance of this emu in the sky will come clear in a moment. If you want to look at the sky, for many, many years, of course, we just looked with our naked eye. But then Galileo, 400 and a few years ago, put a telescope to his eye in St. Mark's Square in Venice and looked at the night sky. And off we were, building bigger and better telescopes. At first, only working in the optical light, in the vision that we talked about earlier. But then, after the Second World War, we went into the world of radio astronomy, and as I've explained, it's because the radio waves are the only other ones, other than the visual light that we see, that actually gets down to the surface. Any other sort of wavelengths, you have to put a satellite up with a telescope that's working in that wavelength. So here we are out in radio land. Just to remind you how different things can look when you look at it with different parts of the spectrum, one thing you can do, just the way we looked at those flowers, and we could see them either in just with our vision, or, and I should have explained this, forgive me, the way we could see the flower, for example, with two colours, was it been photographed with a camera that saw ultraviolet light and converted it into a false colour we could see. So this is us looking at the largest of the planets, of course, the amazing Jupiter, with its red eye, a huge cyclone that was actually seen by Galileo. So it's been going for 400 years plus. The weather forecast, if there were one, would be identical every single day. Stormy yesterday, stormy today, and stormy for a long time to come. So this is looking with our eyes. If we look with a telescope that detects ultraviolet light, and maybe if we could train kangaroos, they'd be able to see this. This is what it looks like. It looks very different. It looks very different because now the light from deep down, the ultraviolet light, can penetrate those superficial clouds, and now we can see it. When the ultraviolet is converted into the violet, we can see. Don't worry about this. That's just a moon that's passing by. But here, you can see, you know, if you get a stone and you flip it across water, if you're lucky, it bounces and bounces. So something has bounced into that planet and disappeared deep inside it. those bruises, so to speak, were not on the surface of this planet a day before. And I wished I'd known it was going to happen, because astronomers were all glued to their telescopes to see it. Any idea what it was that would have bumped into Jupiter? I think there are two things it could be. It could be an asteroid, something that circles round our sun, can take a long time to do it. A very famous one comes back every 76 years. Comet, absolutely. This was Comet Shoemaker-Levy, after the two people, amateur astronomers who'd seen it, and there it was, bouncing into the planet. You can't see it with normal light, you can see it with ultraviolet light. Now let's look at the night sky as if you've got a fisheye lens and you're lying and looking up at the sky. And we're looking at what in the northern hemisphere we would call the Milky Way, because we're looking along the axis of our galaxy towards the black hole in the middle. And that's why Australia is a brilliant place to do astronomy, because the southern hemisphere, we look towards the centre of our galaxy. In the northern hemisphere, they sadly look at the rather boring outer third. So that's why astronomy happens so much preferentially in the southern hemisphere. We can see, if we use the right wavelengths, right to the centre of our galaxy. So here, these are all stars, but the dark areas, there are stars beyond them, but we can't see them because these are dust. They're dust clouds that are going to form new stars, new galaxies in their own right with time, but at the moment are just clouds obscuring the more distant stars. And I showed you earlier an emu in the painting. The Aboriginal people looked not at the bright but at the dark, and they saw an emu in the sky. The South Americans see a llama in the sky. And the time of year when, as the Milky Way in the northern hemisphere, but the emu in the sky for us, comes above the horizon, and it looks as if the emu is actually sitting on the surface of the Earth, and imagine there are rocks around her, they would be like her eggs. But that tells the Aboriginal people that's the time to go and collect the emu eggs. They make the best cakes. So this is looking with our eyes. Now let's look with an infrared telescope. Now we can see right through all those clouds. The infrared penetrates those dark dust clouds that we couldn't see with our normal light, and there in the middle there is towards the centre of our galaxy, where there's this enormous black hole that actually stops all light escaping. Now you can see, if we go back one, you'll notice two smudges here, the larger and smaller Magellanic Clouds. But they show up a lot more in infrared. They're the two satellite galaxies that are circling around our galaxy. And this larger one, we have a very special family connection, because our main house is at Mandurah and we always watch the night sky. In fact, it was a decision whether to buy a telescope or evening chairs and a sofa, and we decided we'd have a telescope and sit on the floor. And so the kids my daughter, then aged 8, came running in one night and said, "There's a bright star in the Magellanic Clouds, Mum." And I went, "Yeah, it's made of stars." She said, "No, it's a really bright one." And that was a supernova that had exploded. And we went out and actually watched it as it exploded. It had been seen in Chile, I think, maybe an hour before we saw it. But we saw it for ourselves before anyone told us. So watching the night sky in the southern hemisphere is definitely worth doing. And it was very special for us, the Magellanics. But if you had radio eyes, if Jenny had been able to look with radio eyes, she'd have seen something very different anyway. She'd have seen that. Because these give out masses of information, but it's visible only if you have radio eyes, if you're a radio telescope. So you can imagine, if you put together the information from all these different telescopes, you can see so much more and understand so much more about what's out there in that amazing firmament. So that's why we build bigger and better radio telescopes to look further away across time, because light takes time to reach us. If the sun disappeared, we wouldn't know for 8 minutes. If the nearest star went, we wouldn't know for 4.5 years. We are looking at light that set out before the Earth even began. The length of the universe, we think, is 13.7 billion years. Our sun and planets have only been there for 4.7. So we're looking at light that set out before we even existed. And what always I find rather odd is that it's a bit like an archaeologist looking down. As they dig down the layers, they look at different time. So if you look across the universe, you look back in time. So we have no idea what's going on out there right now. We can't know. We can only see its history. Anyway, I'm sure many of you will recognize this telescope because it did one of the most important things. It's Parkes telescope. It watched perhaps the most cited bit of TV footage from the previous century. It looked at? Yes, men landing on the moon. And of course we all love the film about it, The Dish. And we were very lucky because as chief scientist I met Buzz Aldrin, one of the two, of course, who to step onto the moon, because he came to Carnarvon to acknowledge that there were 14 sites around the globe that followed the Apollo mission, but only 2 had the continue or abort ability, the signal to send to continue the process or to bring them home. And that, of course, was Houston and Carnarvon. So it's great that he came. By the way, his mum's maiden name was Miss Moon, so I think he had no option but to go. And he was the only astronaut in the whole series that wasn't part of the military. He applied and didn't get in. He went off to an Ivy League university and did a PhD on how to rendezvous spacecraft. He was the only one who knew how to do it, and if they wanted to go to the moon and detach a lunar module and bring it back, they needed to have this gentleman's expertise, and that's why he joined the program, and that's why his nickname is Dr. Rendezvous. Bringing to the more modern times and going back to radio astronomy, if we can build bigger and better telescopes, we can look further back in time, we can understand more. You can't make radio telescopes bigger, they're too difficult to maneuver, they'd fall over. You need to build lots of small ones and join them up by fiber optics, and you need lots of countries on board to do it because it's mega expensive. It's one of the big science projects for the century, Large Hadron Collider being the other one. So these are the countries on board so far. You can see the United States of America isn't. It's building an optical telescope in Chile right now, but we hope it'll join later, and it is in parts of the program because it's the square kilometre array. The whole idea is to build enough radio telescopes that when you add up the collecting area of all those dishes, it would be 1 square kilometre, an awesome sized machine. Where were we going to put these radio telescopes? Well, we spent 5 or 6 years debating this, and I spent a lot of time as chief scientist touring overseas, talking to Canberra as the decision was coming close. And then they did, I think, the very best thing and decided to build it in 2 places, in South Africa and in Australia. Because the world's a very small place, and to have it in 2 continents, I think is a brilliant outcome. And you'll notice that most of what we're going to build will be in the Murchison, but not exclusively. As a result, we have one of the leading centres for radio astronomy research now in Western Australia, between Curtin University of Western Australia, supported by the state government, and I very much commend them for continuing that program despite the financial constraints we have, because we are now one of the world leaders, and we're part of this big program funded from around the world. That must be good. We're building it out, as you could see from the map earlier, in the Murchison. We've chosen this because there are no towns, and we don't need people because they all make radio interference, whether it's your computer, your mobile phone, your microwave oven. So if you have only 110 people, it's very much easier to contain their emissions, and there has to be a lot of discussion with the resources companies to make sure that we don't compromise the mining activities, but still have an exclusion zone that's been put in place by federal and state governments. We've got our radio quiet zone, as you could see. There's me just about to enter it, feeling very chuffed. It's 1 observatory, but 2 missions on 2 sites with 3 technologies. The 2 sites being South Africa and Western Australia. What we're going to do is go out and map the sky. We haven't mapped it properly yet anywhere near. But once you decide what you want to find, what you've seen, you want to go back in more detail and have a really good look. So that's how we're splitting it up: surveying and then detailed look. And that boils down to using different parts of the electromagnetic spectrum, all out in that radio part that you saw at the right-hand end. But the very longest wavelengths, the lowest frequencies, will be detected by two devices. These things here, where we have sets of antennae that look a bit like Hill's hoists that haven't grown up and had their washing put on them yet, but pick up the lowest frequencies. Then we've got survey telescopes. This might look like a conventional telescope, but it isn't. It was designed by CSIRO because instead of sampling one spot, it can sample about 30 times the area of a conventional dish, and the other ones are the ones that are going to look in higher detail. So the two that are being built in Western Australia are these, the Widefield array and the Pathfinder, the survey ones. And South Africa is going to do that, having a really good look once we've decided what to look at. Here are some more photos of the Murchison Widefield array. You can see there are sets of them going out towards the horizon, and there's been a lot of discussion with the Aboriginal people to fully respect their land and their interpretation. And in fact, all the dishes that we have in place have been named by them, which I think is really precious. This is looking at the sun. Not only do these devices listen to the rumbles as the universe formed, the Big Bang, but they can also look when there's a solar flare. Solar flares are really dangerous. They can close down your communications, they can upset your power supply. To know about them early would be brilliant. At the moment we rely on satellites that we put as near to the sun as we can. So this has applied technology straight away. Here we are, we're building the telescopes. We're going up to 36 in the first batch and then to 96. They're actually made in China, so they come down like a huge IKEA flat pack, and somebody spends a month putting them together. They have to be so precise that whatever the temperature, whether it's freezing cold or 40-odd degrees, they change in diameter by less than a millimetre, and they work splendidly. What will the square kilometre array of radio telescopes, they're all joined up, as I say, by fibre optics, do? Here are some of the questions it will answer. It won't directly tell you if life is on other planets, but it'll look at the light that either goes past a planet or goes through the atmosphere of a planet circling another star. And now we know that there are about 1,800 of those at least. And if there are molecules in that atmosphere compatible with life, such as methane, we could detect those. Looking at black holes, cosmic radiation, we hardly understand. Dark matter, dark energy, these are still things we have to discover. And others, we just don't even know what we're going to find. But people say to me, well, why do radio astronomy when we've got so many issues on Earth? And it's a very valid question. I'll come to that in a sec after I've just explained that one of the great things about having this telescope is that it's going to need a heck of a lot of computing power to analyse what's coming through. It's going to produce, when it's fully complete, and that's in 2025, 100 times the current global internet traffic. That's a heck of a lot of information. It's really sensitive. We're using enough fibre optic we could wrap it around the Earth twice. So really this whole project, it's engineering to build it, but by gosh, it's requiring huge computer power. And that's going to be a great asset to Western Australia because we have one of the largest supercomputers on Earth already operational in Kensington. But are we going to get any spin-offs? What's the value of doing radio astronomy? Well, here are some of the ones that touch us every day. If you've used sat-nav to get here or you rely on GPS, you're actually using radio astronomy because the information goes up to satellites, but they wobble a bit. You have to know their exact position. Your reading will be 100 metres out every single day that you failed to correct for that wobble in the satellites. You correct for the wobble, in relation to two very distant galaxies we can't even see except by radio telescopes. So you are using radio astronomy every time you use a GPS or a sat-nav. But if people look inside you, the amazing detail you can now see compared to the old X-rays that were around when I was a girl, that all relies on taking amazing computer programs to analyze very faint signals. That's the same as radio astronomy. But of course, the thing that really stands out that happened from astronomy is Wi-Fi, a great Australian invention. In the 1990s, John O'Sullivan raced 22 other teams of radio astronomers to work out how to take very faint signals and make them more reliable. And of course, it's been a huge income earner for Australia and an enormous, I think, source of pride for everyone. Radio astronomy coming to life. But as I say, it's led to us building one of the biggest supercomputers in the world, $80 million worth. It's down in Kensington. It's powered by geothermal energy, which I think is wonderful. In fact, it's cooled by it. It's drawing up cold water from the aquifers, pumping it through and out the other end. So instead of having an energy bill, a power bill of about $9 million a year, it's well under $1 million by geothermal, which is fantastic. But the great thing about this computer is only a quarter of it is for radio astronomy. The rest can help with meteorological predictions of where cyclones are going. It can predict climate change. It can store all our health data, data from our environment. Altogether, it's offering tremendous potential that we must make the most of. And of course, all the data, for example, all our scientists at the museum collect in relation to biodiversity could be stored there. But we're still not there. The computers we have today are beginning to cope with the problem. But if you work out and go from time, 1993, this is predicting out to 2019, the rate at which computers get better and faster, the faster they get means the better they get, the more capacity they have. The top one is the best computer in the world, then there's the average one, and these little old slow coaches the rest of us have, getting better and better. But now you can see the green is what will be needed for the square kilometre array. So computers have got to keep getting better to keep up, and they have always to date, so let's hope they keep going. And here's an example of putting together data. So that large Magellanic Cloud I told you about that my daughter Jenny saw, the exploding star in that has actually been photographed by the Hubble telescope, and there it is, looking rather splendid as it breaks up into very many fragments. But there's lots more you could understand, and the radio astronomers right here in Perth at the University of Western Australia and Curtin Uni produced this radio image. This is an optical image, this is a radio one, the two spots along our electromagnetic spectrum. And when you put the two together, you understand far more about the processes that happen in a supernova. So a great example of different parts of that electromagnetic spectrum coming together for us to interpret. And here are some other photos of us, of the wonderful artwork that was done as a result of working with the Aboriginal people, but now we feed back images such as the one I showed you in the previous slide, and they inspire new paintings. The final little bit. If we're going to get the next generation of astronomers, of agricultural scientists, we need lots of them, of environmental scientists, we've got to train them in schools. I realised as a school kid, I visited Darwin's house. You can tell I'm a POM before I came to Australia. Best move I ever made. I looked through his microscope. I looked at his specimens. And I wanted to be a biologist. And I kept in my mind, wouldn't it be great if school kids could have their own microscopes? Years 5 and 6 are the ones we need to get at before they leave primary school. For 2 years, I floated this idea totally unsuccessfully, until one lady from Rotary Club put her hand up and said, Rotary can do that, working with the Water Corp and the science teachers. We are now in almost half of all primary schools in Western Australia, so each year 5 and 6 student has their own microscope. You can see them there. We're supplying them to Timor-Leste, to India and to Afghanistan. Doesn't need many people, it just needs vision and determination. I think it's a wonderful program. This is the launch of it, and as I left, this young man had his microscope on this young lady's head. He was looking at the structure of head lice, and at that point I left. We've even got them to ring a soak. This is in the Tanami Desert. There are 8 students there, and there you can see this young man very proudly with his microscope. It's a wonderful program. I'm so grateful for everyone that's done it. And very much the same mission as the museum, get to people from the very earliest time right through their lives. I'm going to finish with my favourite video. I don't know what this creature can see, but I'm pretty sure it can see very well. It's a sawfish, and they're getting increasingly rare. The north of Western Australia is one of the few refuges where we still have them in any numbers, and nobody knew what that rostrum did with the teeth along it in that fearsome array. Everyone assumed that it was using it to guddle along in the sand and just stir up little creatures to eat, until this movie was taken by a fantastic lady working at the University of Western Australia. There she is, Barbara Workinger. So I'm going to show you this video twice because you won't spot everything the first time. A fish is going to come into the top left-hand corner. For those who are sensitive, it is deeply anaesthetized, this fish. And you'll then see how the creature gets its lunch. It has taken the fins off that fish, so it's then hopeless on the floor, on the surface, and in it goes. I'm going to show you that again, because I think it's worth seeing twice. It is extraordinary, isn't it? So we need to know this. We need to know this, for example, if we're going to have to keep them in captivity and have breeding colonies to get more of them. But we also need to know to stop people doing that, because it's like chopping your arms off. So this is part of an education program. This is what the museum's all about. This is what this lecture series is about: sharing information, protecting our beautiful and wonderful planet, because education and understanding are the way to do it, and that's why I think this lecture series is so hugely important, and I thank you for coming tonight and listening.